Hey guys, we're going to talk about tangent lines and derivatives. Actually, today we're just going to focus on the first part, the tangent lines. Tomorrow with the derivatives part, but tangent lines today. All right, what is a tangent line? Hopefully remember from geometry, but just in case you don't, quick reminder, it is a line that just touches a curve. So like that red line right here that you see in the picture, touches that curve just barely, and it hits it, it intersects it at one point, which is the 0.11 there. Now that curve, we're going to deal with this curve a lot as I teach you the basics here, but it's y equals x squared. That's just a regular parabola, vertex 0, 0, your parent function of a parabola. Our goal today is to find the slope of the tangent line at the point 1, 1. Okay, they're going to give us a point on the curve. We want to find the slope of the curve or the tangent line at that point. Now, there's a problem with that, and the issue is we only have 1 point. You know, if we're going to try to find the slope, usually we go y2 minus y1 over x2 minus x1, but we only have 1 point. So we got to figure out some way to find another point because all we have is that curve. We got to find some way to find another point so that we can find the slope of the tangent line. Because if we can find the slope, we can find the equation. All right, we'll end up computing an approximation of the slope by choosing a nearby point and computing the slope of the secant line. So we're going to try to get as close as we can. I hope you're seeing where we're going with this. If we're going to get closer, like there's point Q, which is right there. If we get closer and closer and closer this way, and also, I should be on the red line, closer and closer and closer, not the blue line, closer this way, we're looking at limits again, which is why this is in this section, okay? But computing the slope of the secant line, choosing a nearby point, and the nearer the better. All right, got pictures here of what's happening with our secant lines. The blue lines are the secant line. If you can see the red line, that's the tangent line. The blue line is, yeah, I can pull it up, that's good. Is the secant line. The secant line does not just touch it once, it touches it twice. And look what happens as as the point Q gets closer and closer to P. Here, that blue line is not very close to the red line. Q gets a little closer, look at the blue line. Q's getting a little closer from the right, by the way, from the right side. And look what's happening to the blue line. It's getting closer and closer to the red line, which is the tangent line. And if we approach from the left, same deal. Approaching from the left this time, there's Q. Q's getting closer around the curve. Q's getting closer, and the blue line's getting closer and closer to becoming the tangent line. So the secant line, the closer you get that second point to point P, the closer the secant line becomes to the tangent line. It's getting infinitely close. We're talking limits again. Okay, so here's the deal. The slope of the tangent line is the limit of the slopes of the secant lines. Okay, so as we approach point P with point Q to the right and to the left, that slope of the secant line it gets closer and closer and closer to the slope of the tangent line. So that's what we want to find is what the slope of the line is. All right, and if you zoom in on the curve, by the way, if you were to take your calculator and zoom in on that parabola, this y equals x squared, and get closer and closer to the point 1, 1, look what's happening as you zoom in. It doesn't actually become a straight line, but it's beginning to look more and more like a line instead of a curve, but it's still a curve. All right, but if you zoom in far enough, it kind of looks like it kind of straightens out, but it doesn't. All right, let's go through this thing. Y equals x squared. There's our parent function right there. That's what we've been talking about this whole video. We talked about we want the slope or the equation of the tangent line that goes through the point 1, 1. Any other point, the point Q, is going to be x and x squared, because think about it. Whatever you put in, you're putting in for x here, and your answer for y is going to be x squared, because that's what the function is. The function is y equals x squared. So whatever your x is, just like I picked the point 1, 1. 1 is the x, 1 squared is 1. I could pick the point 2, 2 squared is 4. So that's 1 point that Q could be. All right, but we're going to use Q as just x and x squared because that's what the function is. Okay, so the slope is going to be the limit as Q gets closer and closer to P. Okay, so what we know is if we find slope, you do y minus y over x minus x. So I took point Q right here, and I did y from Q minus y from P. So y minus y, I also did x minus x on the bottom as x approaches 1. And the reason that we're doing x approaches 1 is that's what the point is, that's what the x coordinate is in point P. All right, now I'm going to factor the top, factor the numerator right there, because when I do that, it cancels with my denominator, and I just get the limit as x approaches 1 of x plus 1. And to work that out, you can do direct substitution. You can plug the 1 in right there. 1 plus 1 is 2. So that's the slope of our tangent line, right? Y equals 2, because that's as close as you can get to point P. All right, so if I have this point, 1, 1, and this slope, you can do point slope form from way back in the day. Y minus 1 is 2 times x minus 1. And if you simplify that out, there's your slope of the tangent line. All right, so kind of crazy. I'm going to show you 2 examples coming up, and hopefully after that you'll have it made. I guess an official definition here. No matter what the curve is, we just looked at one example, but no matter what kind of curve you have, here's point P again. Point P is going to be known as A, some number, some point. F of A just means you take the x coordinate and you plug it in. Q is going to be x and f of x every time. X is a number you plug, is just x. F of x is the function, okay? F of x is the function. So if you were to do f of x minus f of a, you would get this side. If you do x minus a, you get that side. So the slope is right there. The difference of f of x minus f of a over x minus a. Basically the slope formula. All right, that's kind of a complicated curve there. Okay, so, and here's what's happening as we talked about it. As Q gets closer and closer on the curve to P, the better the secant line is, the better curve we can have. So we want that limit. We want the limit as Q gets infinitely close to P from both sides. All right, the tangent line to the curve, y equals f of x, whatever the function is, at the point, whatever point they give you, is aligned with this slope. And that's the deal. If we have the point and we got the slope, we can do it. Now, one more time, look at how we do the slope. You take the function, the actual function, minus f of a. A is the number we have right there. That's the number we're approaching. On the denominator is always going to be x minus that number, okay, the x coordinate. A is the x coordinate. F of a, by the way, would be known as the y coordinate of the point that they give you. All right, let's look at 2 examples real quick. Like this one says, find an equation of the tangent line to the hyperbola y equals 3 over x at the point 3, 1. Okay, so to get there, we're going to say limit as x approaches 3. It's always the x coordinate. We're getting closer and closer to the x coordinate. The slope is f of x. Remember, f of x minus f of 3. And on the bottom is just x minus 3. That's how we're going to do the slope every time. Now, what is f of x? F of x is 3 over x. What is f of 3? It's right there. It's 1. On my denominator, I have x minus 3. All right, now, if I start simplifying that right there, what I'm going to do, I should have put another limit there. What I'm going to do here is I'm going to multiply the whole numerator by x, whole denominator by x, just to simplify that just a little bit. Now we get my numerator 3 minus x, my denominator we get x times x minus 3. Now watch what happens when I do that. The reason I didn't actually multiply the bottom out is because I noticed something when I just wrote that out. I can cancel the x minus 3 and 3 minus x into negative 1. So it's really negative 1 over x. And then to do my limit, I can do direct substitution because that's rational. Please plug the 3 in. There's my slope. So there's my slope of my tangent line. There's the point. So to find the equation, I'm doing y minus the y coordinate equals the slope times x minus the x coordinate. I'm going to distribute that negative 1/3. That'll be a positive 1. Move the 1 over, I'll get, that's an x, negative 1/3 x plus 1. And that would be my equation of the tangent line right there. Okay, so let's look at one more. Make sure you got it. All right, there's one other way, and really, to be honest, is a better way to find the slope of the tangent line, and that's using this limit right here. That's where we're going to say limit as h approaches 0 every time. H approaches 0 as a plus of f of a plus h minus f of a over h. I know it's been a long time, but this is also known as a difference quotient. We've seen this actually and worked it out, not as a limit. We've actually worked out the work on that before. So here's basically what they're doing. They're basically saying let's let h be x minus a. Like the difference from this point to that point horizontally is a, and they're saying a plus h, which is really what we had as our first x and our second x, right? So they're saying it's a difference in the x's. If this is the point h, that's the point x. It's just a difference. So we'll talk about that more in class tomorrow, exactly why this thing works, but it's pretty cool, and it's one I think you're going to use this a lot. It's going to help you do some stuff as we go on, okay? So Make sure you get that down. That's huge. That's what we're going to use here on out to find the slope of the tangent line. Okay, let's do one. All right, so let's try one here with the new formula there. So let's find an equation of the tangent line to the curve. That should be x cubed, by the way. X cubed minus 2x plus 3 at that point, 1, 2. Okay, so I'm going to go the limit as h approaches 0, and I'm doing the thing we just saw on the last slide. Remember, it was this. It was f of a plus h. A this time is always your x. A is 1, so I'm going f of 1 plus h minus f of 1 over h. That's what I'm about to work out. It's going to be a monster, so hang in here a second with me. It's going to take a minute. So I'm plugging 1 plus h in for all the x's first. So I'm going 1 plus h cubed minus 2 times 1 plus h plus 3. And then I'm going to plug 1 in everywhere. It'd be 1 cubed minus 2 times 1 plus 3. Right, over h. Now, all I did, that step, is I took that 1 plus h, plugged it in, took the 1, plugged it in. That's what all that stuff is. Now, your job, if you choose to accept it, is to work all that stuff out. Okay, so if I cube 1 plus h, I get 1 plus 3h plus 3h squared plus h cubed. I'm going to distribute the negative 2 through. I got a plus 3. And my bracket here, if I work that out, I get 2 in there. There's a minus sign in front, so I get a minus 2. All that's over h. That's a bunch of stuff. So I'm going to try to combine as much stuff as I possibly can here. I have a limit as h approaches 0. Let's see what all happens. Stuff has got to combine or cancel. So I've got an h cubed. I've got a 3h squared. I've got an h and an h on the bottom. Because what I noticed on the top is I had a 1 and a 3. That's 4. And a negative 2 and negative 2. So they're gone. And the rest of it I just combined. Now the next thing I notice is I got a bunch of h's everywhere, and it's a fraction. So what I'm going to do is I'm going to cancel all my h's. I'm going to divide the h on the bottom into the top, and that will give me h squared plus 3h plus 1. All right, now, that's a polynomial. Because it's a polynomial, you can use direct substitution, plug in 0. It just leaves 1. So the slope of that tangent line is 1, which is awesome. But if you read what the problem said, it says find the equation. So now I have a point and a slope. The point was 1, 2. So I'm going to say y minus 2 equals the slope times x minus 1. Distribute that 1. Move the 2 over. You get x plus 1. There it is. Y equals x plus 1. There's our equation of that tangent line. Don't pass out. Don't faint. It's going to be okay. We'll work on it tomorrow like we always do. You'll get it. We're going to be fine. That thing is awesome. An awesome little shortcut right there. And we'll work on it tomorrow. I'll see you then.